So, as we already mentioned a little bit, we will use this slot to introduce you to an exciting project we've been working on in the last couple of months, and that is AI-based anomaly detection on monitoring data. I am Nikolas. I'm representing ComNET, an IT systems provider based in Hanover, and we have different locations all over Germany. ComNET has more than 30 years of IT experience, and as Matthias already mentioned, we're one of the very early and very first partners of Checkmk, and yeah, we've been a gold partner ever since, and obviously I'm not alone.
Yeah, hi, my name is Timo. I'm from the ETOPS, as you can see there, and we are some kind of you could say the commercial branch of the University of Braunschweig. And what we are doing, we are researchers in machine learning and artificial intelligence, how it's also called. And what we do is everything that we know from our research topics, we try to transfer this into industry and into real products in the end. And yeah, this is why we are here and trying to deploy AI also to monitoring.
Yeah, in this project, there's also a third party involved that's represented by this sports car-shaped silhouette at the bottom. This is one of our long-time Checkmk customers, and as I said, they are the ones we have been working with during this project. Unfortunately, we cannot say the company's name, so we will be referring to them as our anonymous data donor for the sake of this presentation. Now, our motivation for this project is actually a problem that many of you may be familiar with, and that is the larger the IT environment gets, the more difficult it becomes to track individual problems. And just to give you an idea of what we talk about when we mean large environment, these are some actual figures from our data donor's Checkmk installation. We're talking about more than 16,000 hosts, more than 1.1 million services, about 8,000 service problems, and that's not counting acknowledgements and not counting Checkmk internal problems like the Checkmk discovery, alerting about unmonitored services, something like that. We have more than 120 notification destinations, so that's 120 individual teams on application level, platform level, infrastructure level, each receiving their own alerts. And on average, we have about 1,500 alarms per day. So on a bad day, this number could go up quite a bit. So what we essentially have is those 120 IT teams basically all sitting on their own island and knowing what's going on their island, but not really realizing what's going on the other islands. But the problem is, IT doesn't always work that way. The problems can be more complex than that. There can be metrics of different hosts involved, and this is usually not limited to just one IT team. And second of all, it can be that unusual values on certain metrics may be an early indicator for an upcoming major IT problem, even if the corresponding service is still okay because the static threshold is not breached yet. And this happened quite a few times at our customer site, where we had a higher value on one metric on the storage maybe, and at the same time, another value on the ESX hosts has gone up, and things were still okay in Checkmk. But after a while, this has escalated to a major IT problem, which in the end even shut down production for a while. So our goal here is, A, to create an overall view for complex IT problems, and B, to reduce the dependency on static thresholds. Yeah, so what's our solution for this problem? I mean, of course, the answer has to be blockchain. Because that's the answer for anything these days, I guess. But alternatively, we could try to do something involving AI. And if you think about it, AI has been helpful in similar situations in the past, so maybe we're onto something here. problem still is we don't know much about blockchain or AI, but luckily we found AI experts, and that's where Timo comes in.
Yes, exactly. So as you might have noticed from this nice joke is that AI sometimes is kind of a buzzword, I would say. Everybody talks about AI and it can do magical things, but I want to clear up a few things here. So first, AI, well, many people talk about general artificial intelligence, which is this matrix or Terminator-like computer machine which is similar to humans. What is actually more on the rise today, what everybody knows or uses, is so-called narrow AI, which is built for one specific task. So you might notice from home assistants, where we have something like speech recognition, autonomous vehicles, where we process image data and try to detect things or predict things in these images, or recommendations engines that help you to individualize your shopping behavior or something. So, and actually artificial intelligence is the big field. In there is the field of machine learning, and one discipline, and this is where the most success from the recent years comes from, are the so-called deep neural networks. And this is basically what we do a lot. So we train deep neural networks and try to improve applications there. And the question came up, how can AI assist in IT monitoring? And that's where we thought of, yes, anomaly detection is basically one of these tasks which has been proven in AI, or where there is a lot of research going on in AI, not specifically for IT monitoring, but yeah, we said, let's try out what can anomaly detection do with monitoring data. So first, let's clarify what actually is an anomaly. And here I have a little test on you. Can you spot the anomaly here? So if you spotted the anomaly, take your hands up. Okay, that's good. Yeah, obviously, it's this one arrow pointing downwards. So what do we learn from that? An anomaly is a deviation from an established normal pattern. So the normal pattern here are the up-facing arrows, obviously. But let's make it a bit harder. So who can spot the anomaly here? Hands up. Okay, what's the anomaly? Just say it loud. The yellow car. Yes, could be true. But this depends on the definition on normality here. So if we say normal is that every of these vehicles is red, then the yellow car obviously would be the anomaly. But we could also say the normality means that we are cars. And in this case, these motorcycles would be the anomaly. So to do anomaly detection, what we need is a clear definition of what normality actually is. And what does this mean then for IT monitoring? So for example, this is some time series data that we have from IT-based metrics like network usage, disk write, memory usage, and so on. And in this data, somebody took the time and labeled this part here as an anomaly, so something where something strange is going on. And yeah, probably this is something that is maybe even to detect, because we can see that right here, probably also some thresholds are breached at some point. But there are also anomalies that look like this. For example, here in memory usage, where we have a quick drop and then going back to this level, which by some expert has also been tagged as an anomaly. And this is something that would be hard to detect with just some static thresholds applied to the memory usage. So yeah, first let me show you a bit how are deep neural networks learned. In a classical way, you do supervised learning. And one example I brought here is image classification, where we have some input image, so obviously some kind of a car, and we put this into some neural network. Then the neural network gives us some output and says, okay, this is definitely for 5%, this is a dog, or maybe a rocket, and for 90%, this could be a sports car. So in the end, even now, this network would decide probably for the sports car. But if we want to learn this neural network and give it more training data, then we also need labels, like we need some person to sit down and write to this image, tag it with sports car. And then we can give this as a desired target output to the network, and then we try to reduce this error between this distribution, and in the end, our network learns something. But the problem here with supervised learning is that labels are mostly costly. So you need really a lot of these images and a lot of data, and you need people that actually say, this is a car. So another approach is self-supervised learning, and this is what we actually use in anomaly detection. Here I brought you an example also from video prediction. I hope it's visible. Here you can see a typical traffic scene where we have some car driving, and what we want to do is we want to predict what happens next by the network. So the output would then be something like this car moved a bit to the front, and we can see this people here that they also moved more towards the street. And this is one example where you use self-supervised learning, because then your target output is basically the future input. So you train, you just have a sequence of images, and as a target you only use the images that come maybe a few seconds later. Then you can train this network and you can make it predict things in the end. Yes. And the cool thing about such approaches with self-supervised learning, and anomaly detection is one of these, is that the labels then are basically the data itself, and so they are free. And that's also one reason why we, for the IT monitoring application, we use this approach, because we have a lot of data which just comes in every second or every 3 minutes. So yeah, why do we choose anomaly detection for IT monitoring? Another reason, except for the labels, is data imbalance. So let me show you a small example. What a neural network does, it tries to classify the blue dots and the orange dots here. So let's say we want to, the orange dots are our anomalies, some representation for that, and the blue dots is the normal data. So what a neural network does is it actually learns some kind of boundaries during training. So it gets this as training data, and then we have this green boundary here, and in test, we just take this boundary, and when there are new samples incoming, where we don't know what class they belong to, we just apply this boundary and then do some classification. So in this case, we would say, this here is normal data, and all the orange outside the boundaries are actually anomalies. And for balanced data, so where we have as much blue dots as we have orange dots, this actually works pretty well. But in reality, and especially for IT monitoring data, it looks more like this, because we have a lot of good data, normal data, and there are only a few samples that we have that are actually like anomalous data, which is a good thing, which means that maybe the environment works good in this case. So, but when we then train a network in the old-fashioned supervised learning way, it would look like this. We get these boundaries, and if we apply these to a test, then we will see we will get some classifications here that would have been anomalous data that are then classified as normal data, and that's bad. Another example for imbalanced data, here we have a few more samples, but still we can see that these boundaries look a bit weird, and yeah, we get again misclassifications. So what anomaly detection and self-supervised learning looks like is more like this. We only have the normal data, and then we try to learn what normality looks like. So in the end, we will get some boundary that looks like this, that we can also steer with some thresholds, like the tolerance of this boundary. And yeah, if we then apply our test samples again, we can see that here it works well for imbalanced data. So that's why we go for anomaly detection, because in IT monitoring, the data is highly imbalanced in this case. So yeah, our solution is anomaly detection. I don't want to go too much into the details, because that's really a lot of mathematical stuff and so on. But our AI basically consists of 2 blocks. One is an encoder block that takes the input data, compresses it down, and then we have a decoder-like structure that decompresses it, and so we try to learn some kind of compressed data representation. So the input here is data that we get from Checkmk. So these are single service metrics that we get out of from a CMC dump. And then we just have this time series for each of these features, could be CPU, memory, disk, and so on, that is going into the network. Here's one example where we have some anomaly going on in here. For example, for disk usage, which is we have some kind of peak, which would be pretty uncommon. And the network was trained to reproduce normal data. So we let this network reconstruct our input, and this would look like this. If we then compare this input, this reconstructed input with the real input, we can see that we have here this difference. And in the end then, we will get some anomaly score out of this network when we get this, or when we compute this difference. And here we will see that this anomaly score is especially high at this point where we have this anomaly. And by applying then some thresholds, we can then say, yes, here we detected some kind of an anomaly. So this is how it basically works. For our proof of concept, we want to find some nice visualization for the output of the anomaly scores. And this is basically how it looks like. We have our IT environment, which is monitored by the Checkmk monitoring server. We then send the monitoring data to our AI dashboard server, which constantly sends the data to the neural network inference server. All of them are deployed as Docker containers. And then we send the anomaly scores back, and then we visualize these scores here so that somebody can look at it and have a nice overview about all the hosts, where are the most anomalies at some point. Yeah, this is also what we plan to do, that we try to make a system where the human is actually in the loop. So which means that the AI helps the IT expert, and the IT expert also helps to improve the AI in the end, which means we need some process that can constantly collect training data. So we have this, our dashboard here. Then the IT expert has the optional possibility to verify anomalies. So to say, this was really an anomaly, and then we get good samples, we have more training data, and more training data in AI always means you have better models. And this is how we try to achieve this constant improvement loop here. So yeah, now let's come straight to our demo, where you can have a first glance at our AI dashboard. So, Nikolas.
Yeah, thank you. Okay, it's demo time. This is the user interface of our AI dashboard. Now, two disclaimers right up front. First, this is still very much work in progress. So a lot of features are still missing. There's a lot of ideas we have that aren't yet implemented. There is still a lot of work going on basically as we speak. And second of all, unfortunately, we cannot show the original data from our data donor due to privacy reasons. So this demo was taken using a local setup with training data. But we have a very similar instance running in the actual environment of our customer, and this instance is actively receiving data from the productive Checkmk monitoring server. So for visualization, we chose these hexagons. So each hexagon represents a host, and the size of the hexagon represents the number of anomalies that have been recorded for a host. Within the same size of hexagons, we have a color gradient, which also is an indicator for the number of anomalies. And from top to bottom, we have a timeline. So at the very top, we have the host with the most recent anomaly. And if we get to the bottom, further to the bottom, then we have those with older anomalies. And let's see if works like a charm. Or maybe it doesn't. Yeah, it does. So this design is rather dynamic. So if we move the mouse over the hexagons, you will see that they change the color, they pop out a little bit, and you can read the host name even of the smaller icons. And if you click on one of those icons, then this window will pop up. This will show the host name again, the number of anomalies, a time distribution for the anomalies, and when the last anomaly was recorded. As of now, we only show host-based anomalies here. So all anomalies on a host are shown as an anomaly on this host. But in the background, we do have the data for all the individual services. So it is possible to show on which service the anomalies have happened. This is just not implemented in the UI yet, but this is definitely coming. Yeah, on the top we have a slider, a threshold slider, and this is for this anomaly score that is sent back from the actual AI. And we can use that to see only the anomalies with a high anomaly score. If we slide this to the right, you will see that there are fewer hexagons and they get smaller. And if we go up even more, you will see only the very abnormal anomalies that have been recorded. Of course, if we have a large environment and we have a large number of hosts, then we need some kind of filter mechanism. We've added that. It's in the very top left corner. You see a filter icon. If we click on that, a menu will show up. There it is. And we can, for example, filter by host name. So if we want to see only the hosts that have a certain include a certain string pattern, we just enter that, like this machine 2, and we see only the hosts that have this pattern in their host name. And also, we can define an exclude pattern. This is what we're doing now. So we don't want to see machine 2.7, and if we enter that, it's disappearing from the view. Another means of filtering is the amount of anomalies that have been recorded. This is the next step. We have a slider for that. If we just want to see the large hexagons, so those hosts that have a high amount of anomalies, we just use the minimum amount of anomaly slider. And if we increase the value, then we only see the large hexagons. Same can be done for the maximum amount. So if you only want to see the smaller hexagons, you can set a filter for that as well. On the bottom, we also see this follow option. That's this bluish border around the large hexagon here. So by default, the dashboard follows the hexagon with the largest amount, the highest amount of anomalies. But you can set this to a specific host as well. Yeah, and finally, all this screens and videos you've seen so far are from the live update mode. So in this mode, the dashboard is still receiving actual data and anomaly scores from our AI and from Checkmk. And as soon as a new anomaly is detected, it will instantly show up in the dashboard. But if you want to go into a deeper analysis, then maybe you want to go back in time or freeze the dashboard in its current state, and you can do that. For example, if you click on this clock icon on top, you can enter date and time and just take a look at the anomalies that have been recorded in the time frame you set there. Right, and now we see if this is actually working.
Yes, that's a big question. So does the AI or the neural network basically detect the anomalies that are in the data? So to do or to have a look at this, we just send some data into the AI where we know that there are some anomalies in there. So this is the data that we send. You can see these blue lines. We here have, for example, 5 different metrics. And the yellow background here means that this is basically a labeled anomaly in this case. So we want to detect those. And the complete overall count of anomalies in this data would be 316. So keep that number in mind. Because if we now look what this machine actually does, we can see that we spotted 305 anomalies. And if we click on it, we can also see the distribution when it happened. And on the slide before, you saw there are like 2 areas where there were a lot of anomalies, and you can also see it here in this time plot, which I guess will be a bit more, get a higher resolution in the future. So the next case, what happens if everything works fine? So data like this, which looks totally normal, and we have no real anomaly in there. So then we, of course, hope that our anomaly detection will not find a lot of data. And as we see, there are like 5 anomalies. So yeah, it's not perfect yet, but we find that these 5 anomalies are actually due to initialization of this whole neural network. So I think we can get rid of these. Another case, which is maybe a bit more complicated, would be this, where we have like 81 labeled anomalies, which appears in multiple matrix here. And maybe that's the key point. The good thing about this AI, it does not look only at individual metrics here and apply threshold. It sees all the metrics of one host and then can make out if some anomalous behavior is in there. And yeah, 81 anomalies, and we detect 79. So pretty close. Yeah, so then to conclude our talk, the current status of this project is, we are in a 3-year research project, and right now we have like half time, so it's 1.5 years to go. Our first proof of concept is what you just witnessed. This is our AI dashboard, and what we do now is we want to collect more data to optimize our AI models. Of course, what you saw there, these examples, they work very fine, but I have to tell you there are still examples where it's not working perfectly yet. So the lessons that we and also ComNET learned during this project is that this buzzword AI is maybe not as straightforward as it's advertised a lot of times. So there are a lot of issues that you have to take care of, that it's actually starting to give you some benefit in your task. So, for example, pre-processing and normalizing of the Checkmk monitoring data is really crucial, that the network can work with it. And what are our remaining aims and challenges? I think the most important part is that we want to use this AI dashboard to add some complementary value to static threshold-based monitoring, like it's done in Checkmk. So we want to be able to detect anomalies that would have gone unnoticed by Checkmk, for example. Of course, we want to optimize the AI model's accuracy, and we want to extend our approach to a lot of different host types and different types of applications that are running on there, and to make it really scalable to different environments. And of course, collect more data to improve the AI. So thanks for your attention, and I think we are happy to receive your questions now.